Welcome to our notes on atomic mass averages, finding an average atomic mass. You're watching this because either you missed this in class or you want to review. Either way is a very good reason. I do want to point out you will find it useful to have a calculator to follow along with in these notes. So pause a moment, find a calculator, even one on your phone, and use that to follow along. Okay. I want to start with just a normal average. Before we get into the special average we use for atoms. So let's talk about who's in the room. So in a typical chemistry classroom, we have 15-year-olds and we have 16-year-olds. And in my classroom, we also have a 41-year-old. So what would the average then of those people, what would the average age of the people in my classroom be? Well, we would take 15 plus 16 plus 41, and we divide by 3. So you do the sum first, and then you divide it by 3. And it turns out that's going to be 24. So my question to you is, does it seem right to say the average person in the room is 24 years old? I hope you're saying, no, that's not seeming even realistic. So what's wrong with saying that the average person in the room is 24? Well, that really only assumes one person is 15 and one person 16. Shouldn't there, since there's a lot more students in the room, shouldn't the 15 count for a little more and the 16 count for a little more and the 41 not so much? Well, actually, yeah. That's the way it really should be. So instead of just a regular normal average like you might have done in middle school math, we're gonna go for a weighted average. We're going to be sure not only is the number average, but it's represented appropriately with the amount for the average. So let's say, I don't know, in a typical classroom, I typically have 17, 15-year-olds, and I'd have something like 12, 16-year-olds. It's not often I have any 17-year-olds, so I'm going to put a 0 there. And there probably is one person in the room who's 41. I don't know who that would be. Anyway, we're going to find a total of that. So 17 plus 12 plus 1. Do it in your calculator if you need to. Okay, that's up to be 30. Okay. Now I'm going to find a percent. And I remind you that a percent is always part divided by the whole times 100. So the part in this case is the 17. And the whole in this case is 30. So I'm going to take 17 and I'm going to divide it by 30. And I get 56% for 15-year-olds. And I'm going to take the 12 and divide it by 30, and I get 40% for the 12-year-olds. Wow, for the 16-year-olds, let's just say that. 0% for 17-year-olds because there's none in the room. And then that leaves 4%. So 1 divided by 30, there we go. 4%, rounding up to the nearest number here. Left for 41-year-old. Okay, so now that we know the percentages, we're going to be able to weight our average. And this is the method I want you to always use when we're finding a weighted average. I want you to do it line by line, and then we'll add up all the totals in the end. But first we need to convert to decimals. So it's 0.56. 15-year-olds times their age of 15 equals some number. And 0.40 times 16 equals some number. And still 0 there. But 0.04, remember, to go from percent into decimal, there's a factor of 100. So you have to move that decimal 2 places to the left. Always. You don't divide by 100. So now I'm going to take 0.56. and I'm going to multiply it by 15. And I'm going to get 8.4. Now don't go thinking I'm saying the average is 8.4 years old. I'm not saying that. We need to do more work here. We're going to take the 0.4 and we're going to multiply that by the 16-year-olds. Let's try that again. I hate it when my calculator doesn't register my fingertips. 0.4 times 16 is 6.4 years old. And still 0 17-year-olds. I'm not even going to worry about that part anymore. That is a 6 there. And then 0.04 times 41. And I get 1.6 years old there. Okay. And now for a grand total. What I'm saying is the average is going to be the grand total of all this. So I'm going to take 8.4 plus 6.4 plus 1.6, and that will give me my grand total. So that's 14, carry the 1, and let's call it years old. There we go. 16.4. The average student, the average person in the room is 16.4 years old. Does that sound like a much better average to express who's in the classroom? Yes, it does. It makes more sense that the average is closer to what most of the people are right there. So, all right. So that is the difference between a weighted average and a regular average. We put more worth towards the one that has more. We had a few more 15-year-olds than 16-year-olds, and we have way less 41-year-olds than either of those. So those are worth more. So there we go. Okay. Let's take a look at chlorine. Okay. So here we see, check out, let's read the graph. Okay. We have a percent abundance, how much of it there is, and we have a mass. And you can see there are 2 isotopes of chlorine. And this isotope 35 is 75% abundant, and this isotope 37 is 25% abundant. And so is it, well, if we have 35 and 37, the average would be 36, right? Well, is that really fair, looking at the size of those bars, to call the average 36? Please tell me no, that does not seem fair. So that, as we did before with the age, let's find a weighted average for chlorine. So again, this is percent abundance times the mass equals like some number. We'll start rounding to the hundredths place. That's a good place to round to. And we do that as many times as we need for all the different masses. So since I have 2 bars, I'm going to do it twice. If I had 3 bars on my graph, I would do it 3 times. We're going to add up the answers, and that's our answer. We're going to add up those, and that's our answer. So percent abundance, and you need to change it to a decimal. So 35 is 75%. 75% change to decimal, move that decimal twice, 1, 2, 0.75 times, okay, I'll do a times sign, times a mass of 35 AMUs, that's just our label, atomic mass units. And then let's set up this one. The next one is 25% abundant, that's 0.25, move the decimal twice, times 37 AMUs, and there we go. So I'll take in the calculator 0.75 and I times it by 35, and I get 26.25 AMUs. I'm going to take 0.25 times 37, and I get 9.25 AMUs. Okay? So I'm not saying that the average is either of those numbers. The average is going to be what we get when we total them. So I get 0.50 AMUs when I add that up, and I'm going to add this up, and I get 35. So I get 35.5 AMUs as the average. Now let's take a look at that. That would be like right here, 35.5. Well, that makes sense. We have so much more chlorine 35. Should it not make up a bigger portion of the average? And we have so much less chlorine 37. The average should not be as close to 37. We have less of it. So we will see if you do this correctly, your average is definitely closer in number to the one you have the most of. And it will be further away from the number from the one you have the least of. So I could even have just guessed from the beginning from my graph. Let me erase what I've doodled here. If I just had to begin again, and all I could do was guess and not calculate what it'd be, I'd be like, well, it's not 36. And it's certainly not going to be between 36 and 37. So it's got to be somewhere between that 35 and 36. And that's where I would have gone with it. And you can see most definitely our answer, our average, is between 35 and 36. Okay, so that's the process, and if you have a bar graph to read, that's what you do. What if you have pictures? Okay, so take a moment, look at your paper, maybe pause the video if you need to, look at what's being shown in the picture. So I see a carbon-12 and a carbon-13, and I see like protons and neutrons in the nucleus, electrons around, and they very nicely give me a summary down here and down here. So you can see they're isotopes, same number of protons, different number of neutrons, so they have a different mass, and that's why that's carbon mass 12 and that's carbon mass 13. Okay, here's what I want to draw your attention to. This one is almost 99% of everything that's carbon, and this one's only about 1% of everything that's carbon. So which one, 12 or 13, should the average end up closest to? By a lot. Hopefully you're saying 12. It should be closer to the carbon 12 than the carbon, than the carbon 13. Okay, let's find out for certain. I need to change these abundances to decimals. So again, I move that decimal 2 places. Even with the 1, fill in a 0. Be very careful about that. Be very, very careful that you fill in zeros as needed. So I have 0.9893 times 12 AMUs. And I have 0.0107 times 13 AMUs. And I put this through a calculator, so 0.9893 times 12. And it didn't like my fingertips again. I'm trying again. 0.9893 times 12. Okay, and I get 11.87. Again, we're going to round to the hundredths just because. And I'm going to take 0.0107 times 13, and I'm going to round that to the hundredths place again, and it's 0.14. And now I'm going to find my average. Okay, so I'm going to just add it up. 7 plus 4 is 11, carry the 1, that makes 10, carry the 1, 12.01. Okay. There's my average, AMUs, by the way, atomic mass units. That's the label. All right. So there's my average of these two isotopes. It's still 12.01, and I hope you see it is, like we predicted at the beginning, it is extremely close to 12, and that's what we expected because that's a huge amount of carbon-12 compared to carbon-13. So our average is 12.01. Now I want to point out on the periodic table it lists carbon as 12.011. And so you can see that this is exactly how we get those masses for the atoms on the periodic table. It's a weighted average of the naturally occurring isotopes of that element. Again, it's a weighted average. The more of one isotope, the more it counts towards that average. And the less of the isotope, the less it counts towards that average. Okay, let's try another one. Oh, look, now it's all organized in a chart. Does that change anything? No, that really doesn't change anything. Okay, so here we have the names of the isotopes, copper 63, copper 65. Here's their like actual masses. Now this time it looks like it's to the thousandths place there. We have their percent abundances to the hundredths place there. And we're going to calculate the average. Okay. And then, like, cover this up. Don't look at that yet, but later we'll check our work and see how close to what the periodic table says we got. Okay. I'm going to work the same way I've done it before. I'm going to take the, well, let's move those decimals. Okay. I'm going to take the mass times the percent abundance and have that equal something, and then I'm going to take the mass times the percent abundance as decimal and find what that equals. And I point this out. Are you like yelling at the screen saying, wait, you did the percents first last time and then the masses? Yeah, but it's multiplication. It doesn't matter what order. As long as I have one mass, as long as these are connected, one mass and 1% abundance and second mass and its corresponding percent abundance. As long as I keep together the ones that are together, the order won't matter. All right, so now hopefully the calculator will work for me this time. I have 6.929. I'm going to multiply it by 0.6917. And that turns out to be 43, let's go to the hundredths place, 43.53. Actually, so we can compare the periodic table, let's go to thousandths place. Sorry for changing my mind so quickly. But we'll go to thousandths place. That way we can compare to the periodic table really well. Okay, and then we have our 64.928, and we're going to multiply it by 0.3083. And there we have 20.017 AMU. And I'm going to total that up. 8 plus 7 is 15. Carry the 1, 4, 5.36. Okay, let's see how well we did. Here's our average for the two isotopes of carbon. We had our average as 63.545. The periodic table says, I've kind of like colored over it. Periodic table says the average is 63.546. So how close did we get? We got really close. What's the difference? Well, the difference may come from two things. Number one, maybe the periodic table rounded less than I did, because the percent abundances only go to hundredths place. Maybe they used numbers that went to the 10,000ths place or something. That would make a small difference, the difference between that 6 and that 5. Or there might be one other isotope of copper out there that is like minutely abundant, like a 0.5. And so it was ignored when making this table, and that's why, but would not be ignored when writing the mass on the periodic table. But I want to point out this is exactly how that mass on the periodic table was found. A weighted average of the natural isotopes of the elements. Okay, one last example. We could also do this as a word equation. So as you can see, I have words, and the best thing you can do when you start one of these is connect the isotopes so that you know what isotope 1 is, what isotope 2 is, if there's an isotope 3, what isotope 3 is, so on and so forth. So let's see what we have. Calculate the average atomic mass for magnesium. Okay, that's nothing important yet. Blah, 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 blah. If 78.99% of magnesium atoms have a mass of, okay, that is one thing connected. So I like to group. So I do. And then 10% have a mass of that many AMUs. Okay, this is a second thing, so I'm going to circle it this time because it's something different. Okay. And then, I even have a third thing here, so I'm going to underline it this time to connect those. So I have 3 different isotopes, but I've connected them now, and as long as I keep them connected, I'm okay. So let's keep them connected. Difference, I hope you'll see, we have 3. We've only been working with 2 so far. You know what? That really doesn't change things at all. We're just going to do 3 rows instead of 2. I have, am I going to write 78.99? Absolutely not. I'm going to write 0.7899%. I strongly recommend that you, in the reading, move the decimal right there in the reading to remind you. That'd be a very good reminder. Okay, and there's a way to check your work. If you forgot to do that, I'll mention that at the end this time. But we're going to move the decimal, and I have 0.7899 times 23.985 AMUs. And I have 0.1000 times 24.986 AMUs. And I have 0.1101 times 25.983 AMUs. Okay, and I'm going to put this through the calculator and hope it can handle my fingertips. 0.7899 times 23.985. Let's go to the thousandths place. 18.946 AMUs. And 0.1000 times 24.986. 2.499 AMUs. And 0.1101 times 25.983. 2.861 AMUs. I'm going to add that all up. Okay. So we've got 16 carried the 1, 20 carried the 2, 15, 23 carry the 2, 14 carry the 1, boom, AMUs. Okay. So there's our average for magnesium. Now magnesium is symbols Mg. You can look up in the periodic table, see how close we got. Again, it doesn't have to exactly match the periodic table, but that's how that number on the periodic table is found. So notice I had 3 lines this time because I had 3 isotopes, and I did myself 2 favors. I grouped, and you can have different symbols, but I grouped what percents and what masses have to be together in the same line, and I moved the decimal in the reading to remind me to move the decimal in the line. One last thing, what if you forgot to move that decimal? Your answer would have been 2,430.6 AMUs. If you were to pause, and I recommend you do this, okay, don't ignore it like you're some genius, because you're not yet. Do take a moment to check. Ask yourself, with a mass of 23 something here, 24 something here, and 25 something here, would it make sense for the average to be 2,430.6? I hope you would say no. That does not make sense. Oh, I forgot. What did I do wrong? Oh yeah, I didn't move the decimal. I hope that's the train of thought. Does it make sense for it to be 24.306 with 23 something, 24 something, 25 something? Yeah, that actually does make pretty good sense. Not 2,430. So if you forget to move the decimal, that's okay. Check your work because it will catch it, and you just go back and move the decimal and then recalculate, and you're totally good to go. But don't just think, oh, I have an answer, I'm moving on. Do take a moment to see, is that answer realistic? 2,000 is not realistic when you're starting with 23s, 24s, and 25s. So, good luck on your practice. That is how we find an average atomic mass. That is how the number is found for the periodic table, and the expectation is that you're able to write out and calculate these. And I just don't recommend doing this in your head or just in the calculator. Do yourself a favor like you saw and write out each line each time, however many lines you need, whether it be 2 or 3, and get that grand total with them all lined up. Do yourself that favor. You'll have way more success if you always follow this technique than if you try to just work it all out in the calculator and hope you have enough parentheses where you need it, and it can go bad so fast. Be very careful. Again, good luck on your practice.